I can hold in my hand. It's fine. It's fine. I can do that. Okay. Hello. Yeah. Good morning, everyone. Uh, Thank you, ma'am, for that very generous introduction. Thank you very much. And before I begin, thanks to the Department of Chemistry for this kind invitation, and also to the very warm hospitality. Thank you very much. So, as ma'am told, like I'll be talking about electrospun membranes. So electrospun is actually a past participle of this verb electrospinning. So something which is made out of electrospinning can be called as electrospun. That's why we use the word electrospun. So electrospinning is a very versatile technique for the preparation of nanofibers from polymer solutions. So basically you start with a polymer solution which actually is pushed through a syringe, and then very high voltage is applied, and then this polymer solution is getting converted into a film of controlled porosity and controlled functionality. So that's what I will be discussing about. So before I begin, how can I get it like full screen? Or is it like this and duplicate? Then PC only. Then PC only means this only it will show, no? Just a second. I will escape from here. Oops. Okay, let me try from here now. Okay, sorry for that technical glitch. So before I begin, I would like to just briefly introduce the place where I am coming from. Christ University is a university, it's a private university in Bangalore. We were established as a college in 1969. And then in 2008, we are converted into a deemed to be university. And then we have 6 campuses, 4 within Bangalore, and then one in Pune and one in Delhi, NCR. So, like in terms of number of students, we are a kind of big campus, like 20,000, around 20,000 students are studying in the campus. So this is where I come from, and then we have like very active science departments like chemistry, physics, life science, and we were well known for teaching before we converted into university, and the research is actually building up now. People of research background are joining as faculty, and then very active research is happening. So this is where I come from. Then about the content of the presentation, I will just try to share with you. I'm not an expert in electrospinning because the electrospinning process is actually more physics than chemistry. So I don't know much about the fundamental or theoretical aspects of it, but the practical aspect of it, as a chemist, as a material chemist, how we can use electrospinning to get functional nanofibers which can be tailored for applications like sensing, separation, etc. This is what I will try to explain. So fundamentals of electrospinning. Electrospun fibers for sensing applications, sensing of pollutants, sensing of food damage, sensing of gases, etc. And then electrospin fibers for separation applications also, for the environmental remedial application. So, and then if time permits, I will share some other works which is not directly related to electrospinning, but is related to fibrous membranes. Okay, so this is the plan. Let's see how it goes. Now, to begin with, I would like to start with a historical perspective. So I think you are familiar with this idea or notion in history, where various ages of our civilization, ages of the progress of mankind, is related to different type of materials, right? So we talk about Stone Age, where we were able to handle stones only. Stones were our materials of use, materials of functionality or utility, then Bronze Age, Iron Age, Middle Age, industrial era, and then now we talk about Info Age also, right? So, I mean, silicon. So within Info also there are like sub-varieties like, Facebook generation and Instagram generation, right? Two different generations. So within that also you have these variations. So what message it tells us? The thing is like our ability to process different type of materials, our ability to design different materials, and our ability to tap the functionality of these materials actually is directly correlated to our technical capabilities or scientific capabilities, right? So if stone is the only thing you can manipulate, stone is the only thing you can design and construct, your ability or your technological advancement is limited to that. The more number of materials you have, the more ways in which you can control the property of a material, the more useful it's going to be, and more customizable these things are going to be. And then also it's very much related to the structure property relationship also. The property of the material is dependent on the structure of the material, right? And how it is related is actually the subject matter of chemistry and physics, right? How tiny variations in the atomic structure, molecular structure, or assembled structures can vary the functionality a lot. So how to do this? How to do this in a very controlled and regulated way is the challenge of any material chemist, right? So having said that, the first example of thinking of what could be the structure property relationship, actually very ancient example from philosophy, Western philosophy. Thales, one of the ancient Greek philosophers, he believed that everything in this world is made up of water. And what is the logic? Because when he sees water, water can be present in three different forms. Water can be present in the form of water, liquid, and it can be present in the form of ice, and when you boil it, it's actually converted into gas also. That's the only material he knows which can exist in all the known three forms of matter. So then he postulated that everything is made up of water, one or other form of water. Only thing is there is a difference in property based on the structure or based on the stage or phase of the material. So this could be the first example of rational thinking about what is the structure property relationship of materials, right? So we came forward a lot, and then we understood a lot of things about the structure property relationship of materials, how properties of materials are dependent on the structure. Now, for example, very impressive example, if you consider silica, silica in different size dimensions, different dimensions can be utilized for very different applications. For example, the glass we use is silica, right? What is the thickness of glass usually? Usually millimeter, right? And then the silica gel you find in the packages where it's used for the absorption of moisture. There also you have some millimeter size particles, right? And then when it comes to micrometer, you have these semiconductor chips and piezoelectric material. Again, it's the same material, silica, SiO2. Chemically, it's same, but very different application, very different functionality also. Then silica nanoparticle, if you take nanoparticle, silica nanoparticle can be used for UV blocking applications, for painting applications, etc. Same material, but a different dimension and a different application. Then you have molecular sieves based on silica, the cage structure. Yesterday sir was talking about the cage structures, right? So with silica you can do that. So see, the same chemical material made in different morphologies, different size, dimension, actually provides very different functionalities and very different applications. So this tells that if you have a strategy through which you can control the size of the material and shape of the material and assembly of the material in a very intricate and predictable way, you can actually decide or design the property of the material. So this is the scope of a chemist or a material scientist in the application related to materials. You control the size, you predict the performance, and use it for the practical applications. Okay, so that predictability or the determinism in that is very important. Now, when it comes to nanomaterial, So how nanomaterials are different from other class of materials? As you know, size-wise, it comes between the bulk state material and the molecular material. So the size is between, I mean, molecular materials are having angstrom level size, while the bulk state material are having micrometer or even millimeter size. So if the size is in between these two, between the angstrom and micrometer, the materials start showing very different properties which are very dramatically or drastically different from the properties of either molecular material or bulk state material. And not only that, for example, gold, as you know, is a very shiny yellowish type of metal in the bulk form, right? But when you make gold in the nanometer dimension, what is the color of gold nanoparticle solution? Anyone knows? Could it be yellow? No, not yellow. If that's the case, I won't ask this question, right? Yeah. So then, what could be the color of gold nanoparticle solution? Red. Yeah, somewhat similar to red. Yeah, usually pink to red you can change. Yeah, usually it is purple, some variety of purple, right? So again, since you told pink to red, right? What does it mean? So if you ask the color of bulk gold, it cannot be pink, red to yellow. It's always yellow. But gold nanoparticle can have this, variety of sizes. So variety of colors. Actually, this color can be controlled if you can do synthesis of gold nanoparticle in a very precise way. So if you can control the diameter of the gold nanoparticle, the surface plasmon absorbance changes, and then once the absorbance is changing, the color also is changing. So the nanoparticles usually have size-dependent properties. That's why people are interested. You can actually make them in a particular way. Whatever property, whatever photophysical property you want, you can actually control it by controlling the size of it. Another one, it actually has shape-dependent property also. So size is not the only thing. If you can control the shape of it, for example, gold nanoparticle and gold nanorod, they are having very different properties. Gold nanorod is actually having two absorption peaks, while gold nanoparticle will have only one absorption peak. So the same material made in a different shape will have a different property. And then self-assembly. So if you talk about nanomaterial, so if individual nanoparticles are having one particular application, we can never use a single nanoparticle for a practical application, right? We are not, walking around with a nanoparticle to apply somewhere. We cannot handle it actually. So we can handle only assemblages of these nanomaterials. You need to have a bulk state assembly of this nanomaterial, and then the property of the assemblage can be different from the property of individual materials. The way in which you arrange it, just like people, right? When you're sitting here, your property is different. But when you're sitting in a party of your colleagues, your property is different, right? Just like that, the assembly of nanomaterial, the total group collective property is very different, and then that can be controlled in the way in which the assembly is done. Okay, so they have self-assembly related property as well, and also they have very different bio-nano interface. How this nanomaterial interact with biological system is very different from how the bulk state material are interacting with. For example, silver nanoparticle is known to have very good antimicrobial activity, antibacterial activity, which is not present in bulk state silver. And then you can actually control that activity also by controlling the size and surface functionality, etc. So yeah, actually I should have started with surface. The most important property of nanomaterial is actually the surface property of nanomaterial. Why? Because once you make material in the nanoscale dimension, most of the atoms are surface atoms in those systems. This you already know, right? You might be studying in your syllabus. So in bulk state material, if you take the percentage of atoms on the surface, it's very minimal. And it's not having significant contribution to the overall property of the material. But in case of nanomaterial, the overall property is decided by the surface atoms only. So the properties of nanomaterials are actually very much dependent on surface, and even very small changes on the surface actually can change a lot of properties of the nanomaterial. So surface of nanomaterial also is very important. So basically scientists, technologists and people who are doing research in nanomaterials are very much interested in them due to these surface property, size dependent property, shape dependent property and self-assembly related property and bio-nano property. This is very much different from what bulk state materials are having. Now coming to nanofibers. So what are nanofibers? Nanofibers by definition like fibers which are having diameter within the nanoscale dimension, diameter within 1 nanometer to 100 nanometer. That is a loose definition of that. Okay. So what's the difference between normal fiber and nanofiber? Size is there, but usually just like how you have size dependent or shape dependent property of metal nanoparticles, you don't have that type of a property for the size dependent property for the nanofibers. But what's special here is like when you have this assembly of these nanofibers in the form of a membrane, the porosity usually comes within the nanoscale dimension. So the porosity in nanoscale dimension actually is a nanoscale vacancies, right? Nanoscale absences. And if you can control this porosity, so like the presence of certain things are absence of certain things are very much important, like the presence of certain things. So you have nanoscale like people also, right? Absence of some people makes us happy and vice versa also. Okay, so nanoscale nanofibers, when you assemble, you can have nanoporosity. This nanoporosity can be controlled, and then this porosity behaves in a very different way than the normal microporous membranes. So that's why they can be used for many different applications. In context of electrospun nanofibers also, this is actually what makes that system very important, because when you do the electrospinning, you have this membrane and it's made up of nano materials, and then the porosity, the gap between them, between the fibers, can be controlled by adjusting certain parameters of this fabrication process. I will come to that, you will understand it more there. Okay, now coming to fibers, fibers, we have a very long history of using fibers, like centuries of history we have about using the cotton fiber, silk fiber, many natural fibers for practical applications, right? So the central or core property of the fiber is like they have high length to thickness ratio or aspect ratio, more length than the width. This is the idea. And then they have flexibility. They are, if you go for natural fibers, they are economical and they have sufficient strength and length. They have tenacity, that means the resistance to mechanical force, and then most importantly, you have the dyeability also. Dyeability means you can actually incorporate chemical compounds into this, thereby making color to that and also other functionality to these fibers. So that's what makes fibers very interesting class of material. And then, yeah. Okay, so there are natural fibers and synthetic fibers. They can be classified according to the chemical composition, according to the strength of it, according to how flexible it is, how stretchable it is, etc. And also another way of controlling the property of fiber is you can actually start with a normal fiber, you can coil it, the strength of it increases, right? With that coil you can actually make, if you have two coils together, coiled together, you have a yarn, and with the yarn, if you are actually doing the fabrication of cloth type of structure, you have fibrous substrate, right? So it can be like very, very strong because it can withstand a lot of weight if you carefully design the structure of it. So this is why people are interested in investing on fibers. Okay, now about the modifications. As material chemist and material physicist, we are more interested in how to control the properties of fibers. So two type of modifications you do. You can do physical modifications and you can do chemical modification also. So the physical modification is actually heating, ultrasound treatment, leaching, surface adsorption, heating plus stretching, and also in chemical treatment, you have carbonization, sintering, plasma treatment, chemical cross-linking, mineral deposition, etc. So chemically or physically, you can change the property of the fiber by appropriate treatments. Then I think I will directly go to our topic without wasting much of our time. So, sorry, I'm not very practiced with this thing. So I just remember something which I read, not related to chemistry. Kathak, right? Kathak is traditional dance form from Orissa, right? Odisha. So most of the postures in Kathak is a two-dimensional posture. They don't do this more often. They do mostly like this. It's because most of the postures are taken from these sculptures in this Konark temple. And it's very difficult to make, a sculpture which is actually pointing the hand forward. I don't know if it is true or not, but I read it somewhere. So just like that, my gestures are kind of, I can't do this. My gestures are fixed here. So, yeah. So that means like if my talk is boring, huh? No, I think like the voice is not reaching. No, it's okay. I just wanted to share something which crossed my mind. I'm okay with it. No issues. I'm not going to do a dance. Yeah, but you can. I mean, if you feel very excited about the topic, you can dance about it also. But don't run out. You can run out also. That's another physical activity. Listening to this. Okay, fine. Okay, electrospinning is a process or a fabrication technique which is used to make nanofibers. How you do it is very simple. Conceptually or procedurally, it's very simple process. But my students will not agree, because they are the one who are doing in the lab, and then I am the one who is pushing them. It's not easy to standardize the parameters for this, but conceptually it's very simple. Electrospinning, what you do is you have a polymer solution. Okay, so this polymer solution is filled into a syringe. Okay, and then the syringe is connected to a very small syringe tip, which is called spinneret in the technology, in the terminology of electrospinning. And then this spinneret is connected to a very high DC voltage. And then this polymer solution is mechanically pushed down with a controlled force. Usually you use a syringe pump. Syringe pump actually can exert a controlled amount of force at a given time. So usually it's given by like this much milliliter per minute. That is a unit of this, flowing of this polymer. So the polymer is flowing like this, and the voltage is applied, and then you get the deposition of nanofibers. You won't see nanofibers. You will see a film. You will see a membrane, which when you take to the SCM or SCM is usually required, you will see structures like this. So what's happening when the polymer solution is pushed down and electric voltage is applied, that's a DC voltage, two opposing forces are there. One is capillary force. Capillary force want to retain this droplet in the spherical form in order to have minimum energy, right? So in order to minimize the surface area, in order to minimize the surface energy, it actually want to remain as a droplet. But when you apply this voltage, DC voltage, static electricity is built upon. So like, static electricity is increasing. So they are like opposing forces, capillary forces acting in this way, and the electrostatic forces acting in this way. But you keep on increasing the voltage. At some point, this will dominate. Then what will happen? The charge need to discharge. It need to dissipate. So how it can be done? The droplet will come out in the form of a small jet. And that jet is actually called a Taylor cone. From the Taylor cone, the jet is coming out. When the jet is coming out, the solvent in which the polymer is dissolved is getting evaporated. Then what's remaining? Solid polymer. In what form? Very thin, thread-like form. And that thread-like form is getting collected to the collector. Why? Because the collector is connected to earth. You have high charge, and then it want to neutralize. That's why it will get deposited on the collector. Okay, so this you can do in two different ways. One is the vertical format, other horizontal format also. So based on like what type of film you want, this is what you do. Very simple process. You can see this is the horizontal configuration. You can see the spinning tip. This is the Taylor cone from which the fibers are emerging, and then there is this flow towards this oppositely charged electrode, and then the fibers are formed through the evaporation of the solvent. Okay. Now I think a video is there which will explain these things in a more clearer way. You can see the production. And this is a rotating collector. Why we need a rotating collector? Can you use your logic and tell me? Yeah, what is the advantage of using it? Why can't you have a stationary collector? Yeah, so because like if you have a stationary collector like this, the deposition is not happening uniformly everywhere. So you want like very uniform coating and then like a continuous film. So for practical application, it's always better to have a film of uniform thickness. So that's why you keep on rotating it. And then that rotation speed also actually decides the quality of your film. That's another parameter we need to customize. We need to optimize. Okay. So yeah, I was distracting you from the video. So finally, how you get it is like this. One more time, I will play it. Okay, so now it went to a real video. So it's usually on an aluminum foil, and this is actually a very thin film. Usually it's very easily detachable if it is a thick film. And then you can cut in appropriate size, and then that comes as a freestanding film. The thickness of it actually depends on the deposition time. The more you deposit, more thicker your film will be. Yeah, it's very different. Spin coating, you are just rotating it, and due to the centrifugal force, you have this uniform deposition. Here, due to the application of, and also here the internal structure of that is very different. You have nanofibers. In spin coating, it's just a uniform film without any pores. Yeah. And then like getting the polymer solution to spin as fiber is a very challenging task. Not every polymer will spin. You need to have the right combination of polymer and solvent. You need to have the right voltage. You need to have the right distance between the tip and the collector. Many things you need to customize. Even then, some polymers are not spinnable. In that case, they will be undergoing something called electrospraying. Electrospray means it gets sprayed, and then you get deposition of nanoparticles. That also is useful for certain other applications, but electrospinning and spraying are slightly different. I mean, they are differing in the end product. Here you have a continuous film which is made up of the nanofibers. Okay, so this is how the electrospun membranes will be collected, and then what's happening in a chemical level. So initially this polymer, when you are dissolving it in a solvent, it's actually having very random organization. So the polymer strands are jumbled, not organized. But once you apply this voltage, and then due to the formation of this Taylor cone and this ejection from the tip, you have very good orientation of the, you are achieving orientation of the polymer film. So this is a much organized structure than the normal one. So yeah, this is something which happens. This I already told. Like you have a droplet initially in the spherical format, the spherical shape, which get converted into conical, and then finally into a nanofiber. Okay. Yeah. So why electrospinning is considered or envisaged to be a good technique? When you compare other methods which are available for the formation of nanofibers, drawing is one method. Like suppose you want to make ultra long polymer fiber. So what you do is you start with a polymer solution, come up with a needle, touch it there, and then pull it as long as you can. So what will happen? it will elongate in the form of a nanofiber. Like if you elongate enough, you get diameter in the nanoscale dimension. Advantage is you can have actually very, very long fiber. Disadvantage is it's very difficult to scale up, right? If you want to make such a, a cloth out of such fibers, you will use your entire lifetime to make it, right? So because one fiber at a time only you can prepare, right? It's very slow process. Then you have template synthesis also, like you have patterned openings through which the solution is pulled down, and then the fiber, it's coming in the form of fiber, nanofiber, if the pores are nanoporous. So if these are nanoporous filters through which you can push down, just like there are certain snacks we make like that, right? You have some maida, atta or rice, and then you push it through something and it comes out in the form of different shapes, right? So yeah, similar to that, but doing it in the nanoscale dimension. Then another way of doing it is phase separation. You have a polymer which is dissolved in a solvent, and the solvent is not a very good solvent, and you add another solvent onto that, and these two solvents are not miscible with each other. Then you have an interface, and this polymer is actually having some affinity to the solvent which is on the top. So what will happen? This from the solution, it will move up to the interface, and the interface you get a film, and that film can be in the form of nanofibers if you add certain surfactant, and also some soft templates which actually controls the morphology of the interface. That's one way. And another thing, self-assembly. You start with molecular precursors which assemble in a particular way, and the assembly is formed in the form of a nanofiber. But there actually you have more molecular level control or precision over the structure of it. But again, it's not possible to make such a fiber out of all molecules. So because like the self-assembly, yesterday Sir was mentioning about how difficult it is to control the assembly of molecules. But if you have control, that control is a very precise control. That is the advantage. And then compared to electrospinning, whatever disadvantage you have for all these are addressed, and then electrospinning is superior in that. You can actually scale it up, you can actually mix the polymer together, and you have a composite fiber. You can add some nanoparticles into this, so that this property of the nanoparticle also is incorporated into the fiber. So all these advantages we have when you use electrospinning. Okay, so yeah, this is a comparison between different methods for the preparation of nanofiber membranes. Drawing, template synthesis, phase separation, self-assembly, and electrospinning. And can this process be scaled? Among these, only electrospinning can be scaled up. You can do it in an industrial scale also. You can actually have a machine where you have multiple syringe, multiple needles, multiple spinnerets working together at the same time. Then you suddenly get large area of the fibers. So it's perfectly scalable. And is it repeatable? Yes, all these are repeatable. Once you customize, once you optimize the condition, you can actually repeat it. And then is it convenient to process? These four are. Phase separation is not. Why? Because you use large amount of solvent. And also if you want, like say 1 meter square of this film, you need to have a beaker of 1 meter square radius, right? You need to have like 2 layers of solvent, large amount of solvent is used. Also, once the film is formed, how to separate it from the interface? It's a challenging task. Then control of the fiber dimensions. You have very good control when you are using the template synthesis. Just like that patterned opening, the diameter of the membrane depends on the opening size. In electrospinning also you have very good control once you optimize the electrospinning conditions. Other places, for example, phase separation, you are not directly controlling the size of the fiber, and self-assembly also, it's a self-regulated process, and we have less control over it. So you can see a tick mark is there for electrospinning in all these categories. Not just because I'm talking about electrospinning. Tomorrow I will go and give some presentation about this. All this tick mark will be moved. It's not like that. You can question me also if you feel like I'm very biased about my own work. Okay. Okay. Then are we doing good with time? Oh, I think up to 11 o'clock, right? So I will try to finish as soon as possible. So yeah, here. When you do this spinning, you can actually use different type of needles. For example, if you have a one needle inside another needle, okay, and then it's connected to the outer area is connected to one syringe, inner area is connected to another syringe. Now now when the fiber is formed, you have a core shell structure type of fiber. So you can actually think of all possible designs for the needle. Different type of openings, different type of combinations of needles will give you different morphology. Another one, you can think of needleless electrospinning also. You don't always need a needle. You can actually use, cylinder spinneret. You have a polymer solution. This cylinder is moving like this, and then voltage is applied. So this solution is just converting into a film, and it's actually thrown out like this. So different type of spinnerets you can use. This is called, the other one which I mentioned is like coaxial. This is a biaxial syringe. You can see this solution is passing through this needle, and this is going to be like this. So the core of that will be this solution, and the shell will be this one. And you can actually build it on. I mean, like you can have triaxial also. Different type of combinations you can have. So you have like total control over the composition of the polymer film. That's the message I want to tell. Then what are the things you need to optimize for this? You need to optimize the concentration. So 3 different parameters. One is solution parameter, other is process parameter. The final one is surrounding parameter, surrounding conditions. So about the solution parameters, you need to control the concentration of it. How much gram per milliliter you are dissolving it in the solvent. And then solvent volatility, how volatile your solvent is. Then dielectric constant of the solvent. Is it polar, non-polar, polymer is polar or non-polar. Normally you cannot use water as a solvent, because water itself is having very high dielectric constant, which actually messes up with the voltage which you are applying through the DC. So it's not a suitable solvent. Also water is evaporating very slowly, so you will not get quick evaporation of it. You may need a heating condition also. So usually non-polar solvents and volatile solvents are giving you good results very easily. But certain polymers are, suppose you want a conductive polymer nanofiber film. It may not be soluble in hexane or toluene like that. You may have to use some polar solvent also. And sometimes you may have to mix the solvent so that you get a appropriate polarity for the process to happen. Okay. Then process parameters, electric field strength, how much voltage is applied, flow rate, with what speed this solution is pushed through the needle, and tip to collector distance, between the tip and collector, how much distance is there, and syringe diameter, how much big is the opening of the syringe, and electrostatic potential. Then these are the most challenging, and these are the things which students don't like at all, because if you do the experiment today, you optimize it for certain condition. The same condition, same parameters you are using tomorrow, you may not get good quality fibers, because the humidity is not in our control. Temperature is not in our control. Then pressure, atmospheric composition, local atmospheric flow also, like if you have a fan or AC, and then like if your system is an open system which is exposed to the environment, exposed to wind and all, you will not get same results always. So you need to maintain the atmospheric conditions as consistent as possible from experiment to experiment for the consistency of your results. Okay, history of this. Actually, we had a history, very long history of electrospinning. In 18th century, one scientist, Stephen Gray, he was the first one to observe electrohydrodynamic atomization of water droplets. Water droplets is actually evaporating when you apply voltage. And also you can see William Gilbert in 17th century reported the formation of cone-shaped water droplet. Normally water droplet is spherical, right? But when you apply voltage, he observed like some conical shape is produced in the water thing. And then like, people started building on it, and then we are here. And today also we are discussing about it, because still it's very relevant. So, okay, I'll skip these things. And then why these electrospun membranes are considered as important or suitable for the different type of applications. Usually we can classify it into two categories of application. One is sensing application, other is separation application. So why they are considered as suitable? Because they have a highly porous structure, so which makes like very high surface area system, and it's easy for this membrane to be in contact with your analyte in any form, whether it is gaseous form, whether it is liquid form. The porosity gives better area of exposure, which is actually useful for better sensing. And then large surface to volume ratio. Most of the atoms are present on the surface. And then you can always make hybrid compositions. You mix things, whatever you can mix with a polymer solution, and which is not interfering your spinning process, can be used as a additional component or additional material in the nanofiber membrane. So these are the interesting fact. Okay. Then what are the sensing applications? Usually we do gas sensing, heavy metal sensing, and also food quality monitoring. So food quality monitoring is a very emerging field. What you do is, as you saw in that video, finally you get in the form of a cloth. Okay, so this cloth can be used as a packaging material. And in food industry, people are interested in having this, smart food package. Mean a packaging of the food which automatically tells you about the quality of the food inside. So if the food is damaging, the package color also is changing. So this type of things you can very easily make with electrospun membrane. So if I have time, I will show one or two of that which we made in our lab also. Okay, sorry. Then about optical sensing, like you can incorporate materials which are showing emission, and this emission is sensitive to the presence of an analyte. In that case, you can use actually fluorescence quenching or fluorescence enhancement as a detection tool if you can incorporate that material. And it can be scattering based analysis also, like surface enhanced Raman spectroscopy, which actually people claim like they are able to even detect a single molecule using SIRS. How is it possible to detect a single molecule? Are you studying Raman spectroscopy in your syllabus? No, not yet. Okay, maybe in future you will study. So regular Raman spectroscopy, that also is very difficult. It's not easy to get if you don't have a very powerful laser radiation. Right? Raman spectroscopy is based on scattering, right? When you give radiation to a sample that's getting scattered, the majority of scattering events happens as a elastic scattering, where there is no change in the energy. That is called Rayleigh scattering. And then there is inelastic scattering. Two types of inelastic scattering: Stokes and anti-Stokes. Stokes means the energy of the radiation get decreased after the scattering. Anti-Stokes means energy of the radiation increases. So normally the inelastic scattering is happening less in number. So if you use a normal photon source, you will never be able to detect Raman effect. You need a very powerful laser. Then only you will be able to detect some Stokes and anti-Stokes lines. Okay, that also, regular Raman spectra is limited for a concentration of the analyte in micromolar region. Minimum you can detect is micromolar. But if you have a surface enhanced Raman spectroscopy SIRS platform, where usually you have a nanomaterial or nanostructured surface, where you have something called Raman hotspot. So in this hotspot, what's happening is the electric field of the incoming photon is getting amplified in certain nano cavities. So whatever you give, energy is focused into very small cavities, and if you have even if you have very small concentration of the sample there, you get very high energy from it. I mean very high signal from it, very high intensity signal from it. That's called the SIRS. And then SIRS need this surface enhanced Raman spectroscopy need these nano cavities. So if you can incorporate these metal nanoparticles into electrospun membranes, or you make electrospun membranes and coat it with metal, then you have a nanostructured surface which is very much applicable for the SIRS activity. So how do they, I started from this question, like how do they know it's single molecule detection? How do they claim single molecular detection? If you can detect concentration up to 10 to the power minus 23. That is in the Avogadro number region, right? So, and then 1 by 6 into 10 to the power minus 23. What is that actually? That's one molecule. right? 1 mole contains 6 to the power 6 into 10 to the power minus 23, and 1 by 6 into that much molar will represent 1 molecule. So people are claiming we are detecting 1 molecule, but there is like lot of criticism against it, because like when you do this search, it's not like from every point you can detect 1 molecule. This is like a lottery. In a sample, one area you may get it, but definitely you will be able to detect, nanomolar or femtomolar also. It's very easy. Then electrospun, I kind of deviated a little bit. Electrospun membrane also can be used for the search substrate. How many more minutes I have? I can continue. I can continue up to evening if you. But I have a flight in the evening. That's why. Is it interesting? Do you find it useful? Then I can continue for 10-15 minutes. Is that okay? Yeah. This is what happens. Like if you know fundamentals, and then if the audience is very receptive as you are, not sleeping. I think maybe it's because morning, but anyway. I kept on explaining it. Okay, this I will skip and come back to it later. And then the second set of application electrospun membranes can have is for the separation, because you have a membrane of very controlled porosity through which materials can pass, and then which material can pass through it you can decide by controlling the porosity of it. How to control the porosity? You actually change the deposition time. More deposition means more number of fibers per unit area, and the porosity is smaller and smaller. So you have absolute control over what can pass through the filter and what cannot pass through the filter in the size parameter. And also if you can control the surface chemistry of these fibers, you can make hydrophobic or hydrophilic fibers. If it is hydrophobic fiber, what will happen? The hydrophobic thing will be very easily passing through it, because it's actually having affinity for that. And if you are making it hydrophilic, the reverse will happen. So if you have a mixture of oil and water, which is actually a very serious environmental issue, a lot of oil is being spilled into our water bodies, and then how to easily separate it. So if you have a membrane which is custom made like this, and you pour this solution through it, and then after filtration, oil and water is totally filtered. I mean, oil only is passing through it, means oil is separated from water. So for oil water separation is one thing, and another, people are able to control the size of the pores and also the chemistry of the pores. They are using it for desalination application. Desalination means removal of sodium chloride or removal of inorganic salt from the drinking water, right? So this can be used for that also. That's why a lot of people are interested in this. Then oil water separation, wastewater treatment. Lot of inorganic and organic pollutants are there in water, and if you have some specific adsorption of a species to this membrane, you can actually use it for the that application. And then bioseparation, smart food packaging. This I already mentioned before. Now coming to what we did in our lab, one work which we published last year in Chemical Engineering Journal. So here we wanted to make a membrane which is actually capable of doing oil water separation, dye degradation, and antimicrobial property as well. So these three properties we wanted to incorporate in the single fiber. So intuitively, what could be your plan? The plan is like you mix all these materials which are giving you these properties. So we worked with a polymer mixture which is actually cellulose acetate and polyvinyl pyrrolidone. Into that we incorporated zinc oxide particle and also silver doped zinc oxide particle. Three different systems we studied. The polymer solution is a mixture of either this or this. Okay, Ca means cellulose acetate, PVP means polyvinyl pyrrolidone. So certain polymers, they are not spinnable, but to make them spinnable, you need to add it or mix it with another polymer. So that's why we mix this PVP and cellulose acetate, and these are the optimized conditions. And this is one representative image of the film we are getting, SEM image. And then the instrument we used is this one. This is a custom made machine which we purchased from some company in Chennai. So this cellulose acetate PVP membrane, that's not physically very strong. To make it more strong, you can do some process which is called deacetylation. Deacetylation is this process. It's actually basically a base treatment in ethanol. So deacetylation is happening. You can see the color is changing, but the physical strength is increasing. Also, the hydrophobicity is increasing due to that treatment because acetyl group is removed. Then, okay, so these are the physical characterization, how long they are, how wide they are, etc. We studied. It's actually confirmed using EDX also. Then, yeah, these are just structural characterization. I'm skipping. I'm just going to the application part. So, for the oil-water separation, this membrane need to have a property which is called underwater super oleophobicity. You know what is hydrophilic and hydrophobic, right? Hydrophilic means if you take a glass surface and put a droplet of water, what happens? That spreads on the glass surface, right? But if you take a plastic sheet, you are putting a drop of water, what will happen? That will remain as a droplet, right? Or if you look at the angle of interface between the droplet and the surface, that will be more than 90 degree for the plastic surfaces. And it will be much less than 90 degree for the hydrophilic surface. So that's the hydrophilicity and hydrophobicity. So and then normally when we measure this contact angle for checking hydrophilicity or hydrophobicity, we do it in the ambient condition. But for this application, you need to have this membrane immersed in water, or water will be above it, right? So we immerse that film over here, and we try to put an oil droplet onto it. Okay, then that oil droplet you can see is never touching. I mean, it's never wetting that surface. It's actually repelling the oil droplet. So we have this, underwater super oleophobicity. So this is just like, the droplet which is placed on a lotus leaf. What will happen to it? It's actually just, it will never wet it. Like it's just, going away. So my UP school teacher used to say, like, your brains are like lotus leaf. And whatever I'm telling is just, escaping. It's never getting absorbed. So, yeah. Okay, so then what we did was, I think I have a better video here. So we made a oil-water mixture, which is actually a mixture of toluene, and toluene is dyed with methyl red, a orange-colored dye. And then water is mixed with methylene green, okay? And then this mixture is poured over here, and then it was just kept there for some time. You can see what happens. We are pouring, and the time is shown at the top. Yeah, so it's totally completing, separating with each other, even without application of any pressure. And then we tested, like, if you just keep it like that for hours, it should not mix again, right? So we were able to actually hold it like more than 4 hours. Even after more than 4 hours, it's not coming down. So like it's very simple. You have an oil-water mixture, take it and then pour through this membrane. Oil is separate and water is separate. So we could use it for oil-water separation. And then there are like some technical parameters about like how much is the flux permeation, some calculation about how efficient this system is. Okay, that's one thing. And then we used it for oil-water separation. Now we tested it for degradation of dyes. So we had this zinc oxide also there. Zinc oxide usually is used for dye degradation due to the photocatalytical properties. Since that zinc oxide was incorporated in this fiber also, we were able to do the dye degradation also. So I'm not going to the details of it. Then yeah, contact angle also I mentioned already. Okay, then one more application we looked for. We took pieces of this membrane and kept it in some bacterial growth media. We could see the inhibition of bacterial growth wherever you have this material. It's again because of the presence of silver doped zinc oxide we used. That silver is actually giving the antibacterial property. That's the major contributor, and zinc oxide to some extent also is contributing to that property. So yeah, in summary, we were able to electrospin a membrane which is having oil water separation application, dye degradation application, and antibacterial property also. Okay, I think I can stop here for now. Thank you very much for your kind attention, and I'd be happy to receive your questions. Thank you, ma'am. Yeah, it's a relatively yeah. Yeah. Okay, so the entire setup cost us around 5 lakh only. I don't know, I should say it's 5 lakh only, or it's like water half filled and half empty. No, but actually you can make your own setup also with much lower cost. What you need is syringe pump definitely is required, which can push this polymer solution at a controlled rate. And then DC voltage source, any DC voltage source you can use, but like the voltage usually is in the kilovolt range. So 10 kilo, it's possible. You can make by your own. I mean, if you have a good engineering collaborator, very easily you can make. Yeah. Thank you. Yeah. Yeah. So the thing is, like, once you optimize the conditions, if you're doing the experiment for the first time, every now and then you have to see if the process stopped or not. So because this spinning can stop at any moment, because there can be some cluttering of the polymer. The polymer droplet came out, and before it became a fiber, it can actually become solid and block the syringe. That's one thing. And then in that case, you need to see if it is getting deposited or not. So if you just carefully look at the needle, you can see the fiber going out. And if it is stopping, you need to stop and then remove the block and then continue. Because the fiber, you can actually continuously deposit one layer over the other. So for the first time, you should be very careful. And then once you have all the parameters very clearly written down, you can easily reproduce it. Yeah, thank you. Our case, we used polyvinyl pyrrolidone and cellulose acetate. It's a mixture. Yeah. Okay. That also you can take. But I mean, depends on which application you want. This PVP is totally biodegradable. PVA, polyvinyl alcohol, also is highly biodegradable. But like if you want conductive films, etc., you may have to use this PVDF, polyvinyl. I forgot the rest of it. But like depends on which application you want. If it is a electrical application and all, you may not get biodegradable material. But there are a lot of biodegradable film. So when you talk about efficient for what application? I mean, if you want, say, food packaging application, we cannot use a toxic material. You need biodegradable. But if you want like a conductive surface, you don't want biodegradable. You don't want your conductivity to be affected by biological changes, right? So, plastic is good for outside use. Plastic is not good for eating, right? Just like that, yeah.
Sir, very good topic.
Thank you, sir.
We have learned about nanofibers.
Thank you.
My question is that regarding the same.
Yeah.
I think the first criteria is to select
Yes. Yeah. Yeah.
As you said, the non-polar
Hmm.
will be
Easy to spin. Hmm. Easy to spin. Yeah.
polar.
Yeah.
Okay, then accordingly we have to choose the solvent.
Yeah.
Yeah, non-polar.
Yeah.
That's good.
Yeah. Yeah.
So how about water-based system? It will not work at all.
Water very difficult to work.
That.
Very difficult. Yeah.
When you are taking the example of this,
Hmm.
your system you have used,
Hmm.
this
PVP and cellulose acetate. Acetate. Yeah.
you have characterized the cellulose
We commercially purchased it and then used it, and then after the film is formed, from that we removed the acetate to make it hydrophilic. No, partly it's remaining. 100% is not possible to remove, and we don't need that much because we just wanted this, hydrophobic to hydrophilic transition. So we are not concerned about how much percentage of cellulose acetate is remaining. We are concerned about how much contact angle is changing. So. Hmm. Yes. Yes.
Okay. So then we have to look at the secondary forces there. How would the secondary physical forces are there in the polymer?
Yeah. Very good question, sir. So, there are many works. Like now, two type of porosities will be there. One is due to this entanglement of polymer fibers, the gap, as I told, gap between the polymer fibers. But this fiber itself can be porous. You can make it porous. So, some clever thing other people did is like they incorporated glucose during this process, and glucose also is part of the fiber formed. And after that, this film is taken to hot water. Then what will happen? The polymer is not dissolving, but the glucose is dissolving away. And then you have these individual fibers which are having a secondary pore. And in that way, you can actually increase the porosity. So for adsorption, applications, this is very good. Even our lab started doing something like that. So for heavy metal adsorption, normal films are not very efficient, but when we do this, glucose, sacrificial glucose templated films, you have extra pores within the fiber. That's useful, very useful, yeah.
Like nylons and other polymers, they're very good for
Yeah. We can, yes. People have done it, yes, yeah.
I think they are well-known fiber for
Yeah,
polymer.
yes.
And one of the scheme you have shown that you are using some chlorine water,
Yes.
oil.
Oil, water, yeah.
So what's the amount of chlorine water?
So we use like 1:1. Yeah.
So it won't completely
We are not heating, no, sir. This is just a normal mixture. Azeotropic combination is like we are not heating. I mean, we just want a physical separation, no? So, yeah. Yes, toluene as oil. Just an any oil can be used, but as an example, we just took toluene. Most importantly, that the film should not dissolve away. Toluene is not dissolving the film. If in that case, like we were able to keep it for several hours. If toluene is dissolving the fiber, everything will come down together. So the separation should happen, and the film should be stable. It should not undergo any dissolution. We did not actually see. Our idea is to be applicable for any environmental contamination, right? So if there is, a contamination of water in river, we are not making the contamination. No, it's arbitrarily anything. It can be anything. Yeah. Oil spilling in sea, oil spilling in lakes, oil spilling in rivers. All this is applicable. Yeah. Thank you, sir. I think, yes.
Sir, very nice. So I think these materials are very emerging and new so in this case, you are mixing polymer with some nanoparticles.
Yes.
So what is the role for these nanoparticles and how to do it?
Yeah, so we wanted this photocatalytic dye degradation. For that, zinc oxide was added. And at the same time, we wanted this antibacterial activity. That's why we use silver doped zinc oxide.
Nanoparticles, so based on the functions, you are
Based on the function, yes. Yes.
And how about the stability of this thing? Like you using catalysis or something?
it's stable. Like even last year we made this sample, and then now also it's working. Uh-huh. Yeah, strong conditions. For example, if you add sulfuric acid, it will definitely dissolve. It's just like a cloth. Okay, so cloth, even if it is made up of cotton, due to the thin nature of it and also due to the high surface area, if you use very strong chemicals, you can dissolve it. Strong base and strong acid can dissolve it. But like normal condition, for example, toluene, it's not doing anything to it. We can just keep it like that. Water cannot do anything. Only strongly acidic and strongly basic, for my film I'm telling about. There are like, people make ceramic film also through this. They spin it and then do the heat treatment. Then you have a ceramic membrane. Ceramic membrane can withstand acidity and basicity. Acidity basically. Basicity may not be. Yeah, based on the pH response of the material usually. And surface chemistry. Yeah, thank you. Yeah. So pH dependent stability changes could be there.
My question is related to nanofibers ability of sensing analytes. So you said that it can sense very low concentration of analyte.
Yeah.
By which technique
So yeah, the technique I was explaining was surface enhanced Raman spectroscopy, SERS. So which is basically some metal nanoparticle deposited on a surface, or if you have a surface of nanostructured morphology, you can use it. You mean changing the concentration of the nanoparticle in the film? Mm-hmm. Limit LOD. Okay. So how to find out the LOD for surface enhanced Raman spectra? You just try different. Keep on do the serial dilution, and then keep on measuring the signal. I mean, basically you need to get a Raman signal for a particular function group. So depending on the concentration, the intensity will go down, and then like at some point the peak height is equal to the height of the noise. Then that's your limit of detection. Yeah, so you have a nanostructured surface which is a solid. Then if your sample is liquid, what you do is you place a droplet of your sample there and dry it. After drying, you take to the Raman. Sirs, there is no different instrument. It's just the regular Raman spectra instrument. Only difference is the substrate onto which your sample is supported. So if you have a SIRS active substrate, it's giving better signal intensity. Yeah. How much? Voltage. Yeah, that depends on which polymer. So usually it is in the kilovolt range. So our case, I think we use 30 kilovolt DC voltage. So yeah, it's a little dangerous also. I mean, you should not touch that and experiment with it. You should stay away from it. And usually, you need to have a closed environment because it should not be affected by the change in humidity. It should not be affected by flow of wind if people are walking around, and also if the floor is vibrating. Some instabilities can be there. So it's better to keep it isolated. So this instrument which we have is yeah, I think I don't have a photograph of it. It's like a closed system and usually kept in a silent place. Yeah. 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 Okay, book chapter. Okay, I did not write, my student wrote. So basically, magnetic quantum dot, how it is made, it is you make the semiconductor quantum dot, and then you dope some magnetic materials, usually some transition metals, which are paramagnetic in nature. So at the same time, you have this fluorescence property and magnetic property. So if you want to say detect an analyte and then selectively separate it, this can be used, because this material will be responsive to the external magnetic field. Because like this is moving and attaching to an analyte, and then you are actually applying the magnetic field. So whichever is attached to this analyte is coming and getting deposited near to the magnetic field, right? So you have this multiplex functionality of detection and separation in the same material. This is the idea. I'm very happy that a lot of questions are coming. That means, like, see, only two type of people will have questions, right? One is like, only two type of people won't have questions, will not have questions. One is people who understood everything, and other people who did not understand anything. But like, you are in between. That is the right place for a scientist to be. I mean, you should not think like everything is understood. There is something remaining. Please, please. I think the mic is not working, sir. You can be loud. I will hear, I think. Okay. So I'm not a biologist. So what I know is the antibacterial activity depends on the cell permeability. If the nanoparticles can enter into the cell membrane or not. So cell membrane also is like a fibrous membrane where you have this vesicle type of structure. This amphiphilic molecules, lipid molecules, are oriented in such a way that hydrophilic part is outside, and then another layer of hydrophilic is in the pointing inside. So it's a double layer. So not every nanoparticle can penetrate to that. So the penetration of the nanoparticle through the cell membrane depends on the size of the particle and also shape of the particle. So that's why certain nanoparticles are able to enter into the cell that can kill the cell. But if it cannot enter the cell, it will not. So that's why there is a optimum size required for the penetration, and this is my understanding. There may be more things to that, but this is the most rudimentary explanation for that. Did I answer your question? Okay. Okay, thank you.